going to start today on section 4.1, reiterating what I did last Tuesday to make sure that everybody's on the same page. And here we go with our polynomial function. Polynomial meaning many, many, and nomial terms. These are terms that cannot be combined. They are already simplified to the lowest term. There's also some considerations to a polynomial. It has what? What's the uniqueness of a polynomial? Anybody? Okay. All these males and nobody's even guessing. Okay, it's degrees. It's degrees in ascending, descending order from high to low. And the degrees are, can they be fractions? No, because what a fraction is a radical. That's right. That's right. So it would be non-beneficial to have a fraction as an exponent. Okay, so we have something called the leading term in this case. Oh, if I had the proper thing. The leading term is any coefficients and the variable to the n, and this is the degree concept of that term. It's the whole term. That was part that's different for me. I've never had this happen as an identity, but it is for this particular textbook. And we did our first example, all of them talking about parent functions, all right, so that we know what the degree is and the end tendencies. In calculus, we study what's happening either at the asymptote point or at the extremities. It's where it is going as we increase or decrease our domain. That is a whole study of limits, and that would be our first chapter in calculus, and we'll do a little bit about that at the end of this program. So we had this function here, 2x to the fourth minus x to the third plus 8x squared minus 9x plus 6. It's in descending order, so we're in good shape, and it's asking us to what is the parent function look like. Well, the parent functions are the following. If it's linear, is y equals x. If it's a parabola, it's y equals x squared. If it's cubic, it is y equals x cubed. And if it's quartic, which is what this one is, it's y equals x to the fourth. So the parent function is what we do. In real life, we manipulate it. We can flip it. We can shrink it, we can stretch it, we can make it go faster. All kinds of things can occur in the function, but the parent tells us the initial visual of that function. So in this case, our answer was y equals x to the fourth. And all of my examples are from the homework. All of my examples are from the homework, so that's important too. The next example we did was this guy right here. The graph of y equals 5x to the 6 minus 3x to the 4th plus 2x minus 9 has at most how many turning points? Now, first we have to figure out the degree. What is the degree? 6, right. And then we know that in a function of possible turning points, it's the formula n minus 1. Well, what does n stand for? Yes, the degree of the function. And so whatever the degree is, we subtract 1 and we'll get the possible turning points. Now we know multiplicity takes place, and we'll talk about that in a minute. Multiplicity takes two factors the same, so it'll kiss or go directly through, and we won't have the per se, in this case, 5 turning points. And we'll talk about that. We'll use our graph to double check. So here it says, determine whether the function is a polynomial, and if so, state degree. If not, why? Write the polynomial in standard form, that means in descending order, then identify the leading term and the constant term. Now, we talked about in class on Tuesday that the constant does what? What does it do to the function? That's right, moves it either up or down. It is not so much implemented in the function, but it does move it up or down as if we factored everything else, which you'll do in Cal 2. Because Cal 2, you want the factored form plus a constant so that you can do an identity and replace it. We've talked about that a little bit too. So our function for this guy is f of x equals 4x plus x squared. Is it a polynomial? Yes, it is. It's a polynomial. In standard form, we would have the f of x, because it is a function. They stated it was a function, and f of x stands f in terms of x, where x squared would be first plus the 4x. What is the leading term? The leading term is x squared, because it doesn't have a constant with it. What is a degree? Well, the degree is 2, exactly. And the constant is 0. And remember I said I don't know if it wanted 0 or none. Okay, remember I said that on Tuesday, because I don't remember what it wanted. I wanted the 0. I was intuitive, wasn't I? Whoosh. Because we know everything is a plus 0 if it's not stated. That means we're strictly staying within the format of our parent function. All right, we had this one, and this one was tricky. Why was this one tricky? Because it says in the numerator 8 minus x cubed over 5. Why is that tricky? Is it a function? Is it? Yeah, it's a polynomial. Because it has the F word, what? Fraction. But does the fraction have a denominator with a variable? No. Denominator is a what? What value? 5, exactly. So that meant that we would put it first in standard form by making each an individual fraction. And that would give us a negative 1/5 x to the third plus an 8/5. Is everybody comfortable with that? Okay. Again, you have to think about, is there variables in the denominator? Because that would make it a rational function to begin with, to start. And in this case, it was a polynomial. The leading term is a negative 1/5 x squared. And I told you, you could enter it in the calculator in this form and it would be okay. And then fraction, 8/5. All right. Everybody comfortable? All right. We started with this one, and this one is not a polynomial. Why? Fraction. And we need to look at that in response to what it is. So this is x to the 7th, the square root of it. That's what that is. So it can't possibly be a polynomial. Is everybody comfortable? The index is this number right here. It's an understood 2. So if we wrote it as a singular term, we would say x to the 7 halves, because 1/2 would be the square root concept. But we have a degree of 7 to that root value there. Okay. This is, we went over this one too. We have a definition of the power rule. The power rule gives us the parent function in its state and gives it an amplitude as well. And we're getting ready for the transformations and rotations and all of that stuff. So in this case, we're talking about a times x to the n, whatever degree it may be. So we spoke in class about the reading the function in its term. And this was a generality that I gave you, where A is an amplitude, B is a horizontal shift, and C is a vertical shift. Sign goes with the number. Sign goes with the number. And we stated that. I don't know if I put that on the note, so you might want to write that one down. It's not in the book. This is just the way I know it. How to read what you see. Does that make sense? All right. I did write some interesting things for you on the horizontal shift. And that's on the second page of our notes. So, because we're on the second page. Yeah, I get multiplicities. I didn't do phase shift. I'll add that. Again, not bad. Okay, so our first example was the function of x equals x plus 3 in parentheses to the fourth power. And we look at this argument right here, plus 3. And what that does is shift it to the opposite direction, 3. It's a what? Horizontal. Okay, so we want to look at that in our calculator. I think we did do that on our calculator. Yes? I don't know. Well, we're going to do it anyway. Let's see. Take me a minute. I didn't open it up. Yay! So I have some calculators up here if you would like to borrow it. Okay. Our function keys for anything with a graph are the ones directly below the home screen. And we're going to go to y equals. And my plot is still on. Okay. Make sure that the plots are not highlighted. I'm going to open parenthesis, which is above the number key. I have calculators. Does everybody have one? Just hold on to that one. Oh, did you get one? Oh, you got it working?
Figured out.
Okay, well, that's great. Okay. We're going to open parenthesis and put the x, which is second row, second key, plus 3, close parenthesis, up caret, which is the little up arrow, and we're going to enter. We're going to go to the second one, and we know that the parent function of this guy is x to the 4th. All right, so I have both of my functions. I have the original function and the next function. Everybody there? And we're going to go zoom 6. Always zoom 6. Oh, I have to because I'm always using this thing. So let's see what I have. That thought. It won't get bigger. Okay, so what we see is the parent function is red on mine because it's a second entry. And we can see where it is. Well, where did it move? Well, the vertex is at 0, 0, 3 to the left. Does everybody see that? Okay, so if you have any questions about what is taking place, you always look at some hump of any kind. either lower or upper, and then see where it moved. And you'll get that as well. Is everybody comfortable with that? All right.
Earlier in the notes, when we were looking at like the degrees of the polygons.
Oh, a W?
Yeah.
Uh-huh. And this guy here has no coefficient, and it has and it's a multiplicity. But nobody in my class asked me that yesterday. It's a multiplicity of 4. It's a perfect 4 quadrant. So that means it kisses. If it's even, it is 4, but it's always just going to kiss one time, like a parabola. Good question. Thank you. All right. Any others? That was excellent. All right. We good? Okay. So now we have this guy. Now we notice that we have a what? Growing. Because it's greater than 1, right? So we know this guy has a multiplicity, not of factors, but of amplitude, 7. So what happens to the function is it what? Shrinks. It shrinks because it's going up fast. It's moving fast. The 7 makes it move fast. So we're shrinking, and we have a horizontal shift of -1. Is that correct? And the degree is 5, so that means it goes right through. Odd, a multiplicity, the more the multiplicity, sharper the line looks. And then it has a +1, so that is a vertical shift, what? Up how many? 1. Okay, so I wrote that down, and we can look in the calculator, make sure Elma did a good job. Okay, we're going to clear everything on 1 and 2. And we're going to I'm going to enter the first one as our original. And again, we're just building skill on the calculator. And that's important to me. I don't want you to ever feel you can't double check your stuff. And on the second, we're going to do the parent function. What is a parent function? X to the 5. Oops, sorry. All right. Now we know, and that we have 2 turning points, right? Now we can make this clearer if we adjust the window, and we can. So we're going to go to the window, and we just want to see this guy right here, right? All right. So we're going to go to zoom, and we're going to do box number 1. And what you do is you find where the cursor is. Go higher. Doesn't matter where you put it, just so long you've got the most interesting part there. Oh, darn it. I hit too soon. I didn't make my box. Zoom 6. Sorry about that. I apologize. I'll go vertically this time. Oh, I'm frustrated on my simulator. I'm just going to change this guy. I'm going to do -5 and +5 on my window. And on this guy here, I'm going to put it as -5 and 5 for the Y. And that'll do the same thing. There it is. Okay, So we know the parent goes through 0, 0, and we now to the left 1 and up 1. And we know that this is very laid back, where this one is very strong. So this portion is because of the 7. Does everybody get that? Okay. Now, sorry about that. On the simulator, it's a little bit hard. On my calculator, I can do it all day long. We're going to identify zeros. Zeros are x-intercepts. And what they do is we use it in solving quadratic, solving cubics. All solving has to do with finding zeros. And that means that you've got a function that is equal to something you set, or you will find the x-intercepts. And it talks about r as the value of the zero, r as the value. Depending on what book, it's x equals r. So if we wanted the factor of it, we would subtract r from both sides and have the factor that created that item, that zero. All right. And we'll be looking at our calculator as well. All right. Is everybody comfortable about how to convert zeros into factors? Because that's our first step. Our next step is to find the zeros. Right? Is everybody good? Everybody good? All right. So the first one we did was this guy right here. And they were easy. It says it's a degree 3 with zeros of -2, 2, and 1. So that meant that x equals -2, x 1, because that's where it crosses the x-axis. So now we solve for the factor. So I added 2 to both sides and got a factor of the polynomial. And I had x equals 2, so I subtracted 2 from both sides, and I came up with this factor. I had the last one, x equals 1. I subtracted 1 from both sides, and then I got the last factor. So each one of these is x. So we get the degree 3 because x times x times x is to the 3rd power. Is everybody comfortable with that? All right. And so then we would write it in functional form. Okay, once we get the factors, we stick them together. Everybody good? All right, we're good? See? All right, well then they gave us this one and they included multiplicity. Multiplicity implies the exponent to the 0. The exponent to the 0 that's converted back to its factor form. So here we have a degree 3 with -4 with a multiplicity of 1 and -1 with a multiplicity of 2. So in this case, we had x equals -4, which I added 4 to both sides and got this factor. Has a multiplicity. I'm going to take a shortcut, multi of 1. So that is the factor. Then this one, we had x equals -1. So then I added 1 to both sides and got x plus 1 equals that 0. So I am good on the factor. So this is my factor 2. But it has a multiplicity of 2. So therefore it has the square. Does everybody see that? All right, so now we're going to write it because I stopped right there. So we know that if this is an x, then this is a what? X squared. So we get the third degree if we did FOIL. Okay, so now we're going to write it as a function. That's where I left. I got tired. Everybody was brain dead. All right. All right. Everybody got it? Everybody breathing? I like breathing. All right, this one is given in a very interesting point. And this one, and I probably stopped because of the math on this one. And I thought I'd run out of time. Find a polynomial function with the zeros, -3, 1, and 5, whose graph passes through the point 6, 90. All right, 6 and 90. So here is my point of 690, which is my x and y. So we probably have an interesting scenario here. So let's do first our zeros. There are no multiplicities. So therefore, it's going to be relatively easy. So we have x equals -3, x 1, and x equals 5. Right. So I'm going to solve for the factor. So I'm going to have x plus 3 as a factor equal to 0. X minus 1 is a factor equal to 0. And x minus 5 is equal to 0. All right. Is everybody comfortable with that? All right. So now we're going to structure it. F of x equals x plus 3 times x minus 1 times x minus 5. All right. Now we're going to have a constant here, and what we're going to do is insert a 6, right? Because a point was 6 and 90, right? So we're going to put a 6 in and see what we get. And 90. Oops, and I put 3. I apologize. I make up my own numbers. So this is a 9, this guy is a 5, and this guy is a 1. Is that right? So we need a constant. All right, so we know y has to be 90. So now we have all of it. Oops, forgot my x. Sorry. That's as good as it gets. Make the math easy. Don't do FOIL if you don't have to, right? Mathematics is what you do with it. Everybody good? All right. Now, this one's interesting because it has a y-intercept as -36, rather. So a y-intercept says 0 for x and -36 for y. Is that true? And we have zeros for a 3 degree of -1, 1, and 4. We go. Is everything clear? Like mud or like a stream? Like a stream or maybe a current in the stream. There we go. All right. You all stop me now. This is your class. All right. X equals -3, X equals 1, and X equals 4. That's our first start because these are zeros. And we know they're x-intercepts. So I'm going to add the 3 to keep the 0 concept that was happening when they factored this trinomial, this cubic. X minus 1 and X minus 4. Everybody good? All right. So we got our initial. There's no multiplicities, but we have an output. So we're going to do our f of x has to equal our x plus 3, our x minus 1, and our x minus 4. Okay, we know we're going to have some kind of constant out there, right? And we can put the plus c, but I just like to do the math. So I'm going to do f of 0. I love that. 3, -1, and -4. Well, these two make +4, so it's 12, right? Correct? Okay, but we know we need a y-intercept of 36. So if I subtract 12, I think I get 24. I love this because it's teaching you not to worry about what the constant is till the end, because it's factored. It's negative. Ay, Dios mío. Now, oh, I made a mistake. Thank you. Sorry about that. Hurry. I didn't write the right thing. -48. I apologize, class. All right. Here we go. Ready? Okay. Are we ready? Everybody right. This is your lifeline. All right. This is our last, no, next to the last, I think. Yeah, I think. All right. For the polynomial function of f of x equals 6 times x squared plus 4 squared times x minus 3 cubed, answer the following question. List the real zeros and its multiplicity. All right. Now, if I set x plus 4 equals 0, am I going to have a real 0? No. I'm going to have the I word. Imaginary. Okay. So we know that's not a real. It is a 0. It's used, and I mentioned this in our intro, that in electronic engineering, that's used a lot, is the negative, the imaginaries. But for this one, it asked for real zeros. So we're going to rule out that one, but we have the other one. As a multiplicity. What's the multiplicity? correct? All right, good job. Now we're going to determine whether the graph crosses or touches the x-axis at the x-intercept. What does it do? It's odd. Look at your notes, the ones printed on the second page. Crosses. Great. All right. Determine whether the maximum number of turning points on the graph. Okay. Now, we have a degree. What is this degree on this thing? We have a degree of 3. So we should have 2 turning points. But one of them goes right through, right? So do we have it? Do we have 2 turning points? All right. Could be. I'm not sure. Because it's a multiplicity. We're going to graph it. I am not sure, folks. So it's a very involved function. And I can't swear the answer. Hold on. So our function was 6 times x squared. What was it? Plus 4. And this guy was squared, right? And was it times? Ooh. Oh, wait a minute. That thought. Oh, and it's times. Oh my God. The degree is 4, 7. The degree is 7. Oh. So it's 6. So, okay. So let me get my calculator back out. So the possibles, 6 turning points. I apologize for that. I omitted that this was a multiplication. Now, but has a multiplicity of 2 and a multiplicity of 3. So it looks like 2. I think it's 2. What do y'all think it is? How many turning points do you think it is? Don't know? We're going to find out. This one's a little strange. And I don't remember what the book said on that one. Oh, sorry. Let's try Zoom 6. And I have a giant line, and it's, so we're going to have to, and it's big. This is big because it's going so fast. I would say on the window, let's go a negative 100 and a positive 500. Scale to be 50s. 2 turning points. And that's what I said, 2 turning points. The 2 turning points, okay, because we added the one that had 4, it's squared times 2, that's 2, and then 5 from the 7 was. That's 2 turning points. Well, it's not visible. So that's how I did it. Mathematically, 5 from the 7 because of the multiplicity. Okay, well, I was right. I didn't remember I didn't even think about that for this one. Determine the end behavior that is, find the power function that the graph, oh, turning points too. Okay, the graph of f resembles 4, determine the end behavior. Okay, so we have an odd, all right? And they want to know the end behavior. Okay, if it's odd, then if we're talking negative infinity, it is what? Over here. And then as we go to positive infinity, it is where? So the end behavior, and that is in your notes in a square on the bottom. Okay, it says the leading coefficient is positive, and it is. So it is down, up. It was on the first page. Did everybody find it? Is everybody comfortable with that? Oh, that was a good problem. All right, here we go. Determine whether the graph could be the graph of a polynomial. Yes or no? Yes, it's continuous. It has turning points. It is beautiful. It is a very beautiful function. So yes. If it could be, list the real zeros and state the least degree of the polynomial. All right. So if I looked at it real close, I have a 0. Oops, sorry about that. Okay, I have a 0 at -1 and a 0 at -2 and a 0 at a +4. Is that true? Okay. So the least degree is what? How many zeros? 3. Well, actually, yeah, yes, because we have 2 humps. Okay, everybody good? All righty.